Welcome. So, we have been looking at solving the diffusion equation using variable separable method, and we have solved one of the ODEs, and the second ODE that we want to solve. So, let me write it down: G dot plus P squared dg equal to 0, but from our solution for the first ODE, we know that P squared is nothing but n squared pi squared by L squared. So, I am going to put it here. So, G dot plus n squared pi squared by L squared d times G equal to 0. I am going to call this as some lambda n squared, okay. G dot plus lambda n squared G equal to 0, with lambda n being given by n pi by L root d, right. So, lambda squared will become n squared pi squared by L squared d. So, that is what is here. So, let us solve this equation: G dot plus lambda n squared G is equal to 0. Of course, you know that you can integrate this equation, and the solution will be G n of t will be some constant b. So, let us not call it as b, let us call it some constant k n times exponential minus lambda n squared t. So, this is the solution for this equation, because dg by dt plus lambda n squared g equal to 0. So, you will take it to the other side, and dg by g will become minus lambda n squared t, and dg by g will give ln g lambda n squared g. So, you will integrate it, that will give you, you will exponentiate it, that will give you g of n as exponential minus lambda n squared t plus that constant, and if you assume that constant to be some logarithm of k n, that it will become k n. Okay. So, that is what the solution is. So, ODEs you know how to solve. So, from the solution of this very simple ordinary differential equation, we get this solution. So, we know how to solve the second equation now. So, let us put together the solution now. So, we have the solutions for both the parts, we have solved both the ODEs. So, we know what f is, we know what g is. So, remember C of x t was assumed to be f of x times g of t, right. So, now I know what the g of t is, that is some k n times exponential minus lambda n squared t, and we know what the f of x is. So, that is some other constant b n times, we had the solution sin n pi x by L. Okay. So, let us merge all these constants. So, we have some constant say a exponential minus lambda n squared t sin n pi x by L. So, this is the solution, but the solution is different for each n. So, the most general solution that you can write. So, let us call this solution as C n, because this is for a particular n. So, C is a summation of all C n of x comma t, that is then given by some summation n equal to 1 to infinity some a exponential minus lambda n squared t, and then sin n pi x by L. Okay. So, we have C for all x for all times given by this expression, because there are and n goes from 1 to 3 etc. So, that is why you have this summation. We have this solution, we have not used our initial condition yet, which will help us then determine what this constant is, right. So, and we said that at time t equal to 0, this C of x is a function f of x, right. So, we can substitute that in the solution. So, let us take this quantity. So, C of x comma 0 is equal to f of x, which means f of x is equal to summation n equal to 1 to infinity a t is 0. So, exponential minus lambda n square t is going to give you unity. So, you have sin n pi x by L. Okay. Now, from this expression, let me also write this a n. No, we have not written a. For each n there is going to be an a. So, now all this a n can be determined, because if you multiply by another sin n pi x by L and integrate it over dx over the length 0 to L, then you will get but for some constants a n, and which means you are going to do this same thing on the other side. So, you can find a n to be 2 by L. So, we can do this as a tutorial to convince ourselves that this indeed is so. This becomes 0 to L f of x sin n pi x by L dx. This happens because you know, for sin n pi x, unless the sin, so suppose if you multiply by sin n pi x by L and this n and this n are the same, only then this will light up, all the other cases it will be 0, which means a n will be chosen, and when that sin squared n pi x by L is there with n some value 1, 2, 3 etc., that integration will give you 2 by L. So, I mean L by 2. So, that is why you are having 2 by L here. So, that quantity, and so its integral f of x sin n pi x by L dx, which means this is integral a n sin n pi x by L and sin m pi x by L, right, and only when n equal to m you are going to get some value, and all the other cases you are not going to. So, this is how we determine this constant, and n goes from 1 to etc. So, you have determined the constant also. So, we now finally have a solution C of x comma t is nothing but summation n equal to 1 to infinity a n exponential minus lambda n squared t sin n pi x by L, and a n is determined here. So, this is the solution that we have obtained using the variable separable method. Okay. Now, at this point I want you to go back and remember one of the solutions that we wrote down for the diffusion equation. When we were looking at the classical diffusion equation and its solution, and what happens when diffusivity becomes negative, we wrote down a solution. So, I want to remind you of that solution. We wrote that C minus C naught is equal to some a of beta comma t exponential I beta x. Okay. Now, compare this with the solution that we are getting. We are saying that C of x comma t is equal to summation n equal to 1 to infinity a n exponential minus lambda n squared t. Lambda and beta are related, right? Beta we said is 2 pi by lambda. Okay. So, this lambda, so this is a function of lambda, and here also we said that this is a function of lambda and time. So, you can see that this is just a function of lambda and time, and exponential I beta x, instead we have here sin n pi x by L. So, basically exponential I beta x is a sinusoidal solution, and here you have a sinusoidal solution. Okay. And but for a constant, right, you can add any arbitrary constant that is only going to shift. So, your solution is sinusoidal like this, and with time it is going to decay. So, there is a decay which is involved with the sinusoidal solution, and all this can be shifted by some constant. So, that is all that we assumed in the other solution. So, now you probably understand where this solution came from. This solution, we did not derive the solution at that point. We said that this, suppose this is a solution to this equation, we substituted it back and we proceeded with the analysis. And here I am trying to show you why this assumption that this is a solution for this equation is correct, because you can take the partial differential equation, you can use variable separable method, you can reduce it to 2 ordinary differential equations, you can solve them one by one, you can use the corresponding boundary conditions and initial conditions, and when you finally collect the solution together, you get the form of the solution, which is the same as what we assumed in the other analysis. Okay. So, in other words, so we have looked at the solution to the diffusion equation, and before doing that we actually also showed that the so called Fourier law of heat conduction is the same mathematically speaking as our diffusion equation. And so, the solutions for both are except for symbol differences is the same mathematically. So, heat conduction solutions are also the solutions for diffusion, classical diffusion equation. So, and then we went to the classical diffusion equation, we used a method called variable separable method. So, we assumed that the solution can be split into a part which depends only on position and another part which depends only on time, and we proceeded to derive this form of this time dependent part and position dependent part. We see that the position dependent part is a sinusoidal one, and we see that the time dependent part is an exponential decay. Okay. And this is what we were also trying to plot and show. So, if you look at this solution, so there is this exponential lambda n squared. Remember, lambda n was involving diffusivity, and the diffusivity has some negative value, then this is going to be positive. So, this exponential is going to grow. So, this is what we actually plotted when we did this, and we tried to show that if you take lambda and if you take a look at what happens to the r as we defined, d r by dt as a function of time, how this changes. We called it dA by dt, and it depended on some r, and that actually grew exponentially, right. So, we saw that sorry, this is not the way that was with beta. So, with lambda we found that it grew exponentially as lambda went towards 0. If it was beta, it went like that. Okay, beta is 1 by lambda. So, very small lambda, they also grew very fast, and that is understandable. When diffusion has to take place over shorter distances, it can happen much faster. This is the idea which is related to the non-dimensionalization, which is what we will use to again show you another form of solution to the diffusion equation. Like I said, there is no single solution to the diffusion equation, it depends on what boundary conditions you are going to assume. So, we have assumed some boundary condition for which we have obtained some solution, which is what we have discussed till now. So, there is another way of deriving a similar solution, a similar kind of solutions, but with different boundary conditions. So, which is what we will take it up in the next part of the lecture. After we do that, that involves some non-dimensionalization and some neat ideas from non-dimensionalization. So, we are going to do that. After we do that, we will go back to solving this equation numerically and using finite difference technique first, and then using the Fourier transforms. Okay, so, you can see that already there is some indication of sinusoidal solutions here, and historically also Fourier was looking at his heat conduction equation, and as part of this solution is how he derived his Fourier series. The analysis came from this trying to find a solution for this problem. So, obviously Fourier techniques can be used to solve, and numerically, because there are ways of doing very fast Fourier transforms, and those algorithms help us actually do the spectral solution for these equations quite easily and quite fast and quite efficiently. So, we will do both ways of solving it numerically using finite difference and some spectral methods. But before we do that, we will do one more analytical solution, which is obtained using a transformation of variable, and that transformation depends on non-dimensionalization to some extent. Okay. So, which is what we will take up in the next lecture. Thank you.